Awesome. So Osman, I will turn it over to you.
Thank you. So hey everyone, so I'm going to talk about a new approach to do performance analysis on gem5 O3 core. This is a joint work of David, Pramod, and me. So basically today, all high performance CPUs use out-of-order cores to achieve high performance because they can keep different parts of these core busy. So it is important that we accurately analyze out-of-order cores to efficiently design high-performance cores. However, analysis of the out-of-order cores is a challenging task. So let's start with the performance analysis issues in gem5 O3 core. The first issue is in the high complexity of out-of-order cores. So multiple simultaneous methods can occur in an out-of-order code. So these methods can both like overlap and hide the true bottleneck, hide the true performance bottleneck of the core. So for example, there might be a BTP mess in the fetch stage, an L1D cache mess, and a contention execution unit part in the execution stage all at the same time. However, an out-of-order core can easily hide some of these stalls by simply working on other instructions. Therefore, a high miss or stall count does not necessarily reveal a performance problem on that stall. The second issue is the gem5 out-of-order O3 core is hard to configure. So there are about 50 different parameters for base O3 configuration, and even more is needed for number of execution units, branch predictors, and cache hierarchies. And since it can be easy to misconfigure it, a misconfiguration leads to a misleading performance analysis. And the third issue is that the O3 stats are hard to analyze. So after a simulation, you get something like this. There are like thousands of these stats with no clear guidance and no systematic approach to see which of these matter most. And it is very time consuming, and it can be very unfriendly to the beginners of gem5. So our proposal is adopting top-down methodology, first proposed by Intel. It is an industry-proven method that is being used in Intel V2 and ARM telemetry solution. So by adopting top-down methodology, it will provide a hierarchical and systematic performance analysis method, which can significantly decrease the time needed for analysis. Also, it will correctly identify the true bottlenecks. Moreover, it will bridge the gap between real hardware and gem5. And lastly, this top-down methodology can be used to validate gem5 configurations by simply running the same workloads on both gem5 and real hardware, and then compare the top-down results. So before moving on to the top-down analysis, some background on out-of-order cores. So they consist mainly of two parts: the front-end part, the in-order part, which is responsible for fetching and decoding of instructions, and the back-end part is the out-of-order part, which is responsible for issuing, executing, and committing instructions. So instruction dispatch is the last stage of front-end that happens after rename, and it is the transferring of instructions from front-end into the back-end. And the dispatch slots are the number of operations that can be dispatched in a single clock cycle, which is also the dispatch width of your machine. So let me walk you over the top-down methodology. So we start after renaming the dispatch stage where the instructions will be sent to the backend. So we start with each dispatch slots. So each dispatch slot can fall into either one of the categories. In a dispatch slot, either an operation can be dispatched or it might be unutilized, meaning no operation was dispatched. For if an operation was dispatched in a slot, it can also fall in the retired category, which means the instruction was successfully committed, or it can fall into the bad speculation category, which are the instructions that were scratched due to being on the path of a mispredicted branch. For the unutilized slots, they can be categorized under front-end bounds, which means no instructions could be sent from front-end to back-end, or back-end bounds, which means the back-end couldn't accept more instructions from the front-end. So let me give you a small example on how we categorize the slots into these categories. So in the first cycle, all 4 slots are used, meaning 4 instructions were dispatched, and these instructions were successfully committed. So we add 4 to retiring category. So in the second one, there was a backend stall, and so there was no dispatch in that cycle. So we add 4 to backend bounds category. And then in the third one, there was no backend stall and no dispatch, so 4 to frontend bounds. And then we can have combinations like these. So two dispatch slots were utilized, 2 are unutilized, so 2 to retiring and 2 to front-end bounds. And then in the fifth one, we have dispatched 4 instructions, but the only first two are successfully retired. The last 2 are scratched due to being on a mispredicted path. So we add these 2 instructions to that speculation, and the first 2 goes to retiring. And in the sixth cycle, this is a recovery cycle. So no instructions were dispatched due to a recovery after a branch prediction, a misprediction. So we add these slots into that speculation. Then after that, we calculate the total dispatch slots, which can be found by multiplying number of cycles by your dispatch width. This gives you your total slots. And then we basically divide the number of instructions allocated to each category or the total slots to find the fraction of instructions in each category. And then the highest one will be marked as the bottleneck of your processor. So moving on to level 2, after finding your bottleneck in the level 1, we can drill down into level 2. For that speculation, we have branch mispredictions and machine clears. And machine clears stand for any other pipeline flash, such as a memory order violations. For front-end bound, we have fetch latency and fetch bandwidth, and back-end bound, we have core bound, the contention on execution powers units, and memory bound is the contention on memory hierarchy. And we can even drill down into L3 at the granularity of microarchitectural features for these categories. So moving on to implementation details. Our implementation is in accordance with the hierarchical approach of the methodology. So we have and it can be easily expandable with deeper levels. It's a very lightweight implementation. We have used 15 stats and only 8 new stats are added to gem5. So to understand the top-down output, after your simulation, you will see this in the stats.txt file, like any other statistic. The metrics are grouped in a hierarchical way here, and the statistics are registered for each core. So moving on, at the top, you will see the level 1 results. These 4 categories should sum up to 1, which are like front-end bound, back speculation, back-end bound, and retiring. And then down, you will see the level 2 of each category. And each subcategory here should sum up to their parent. And then there's L3. And then again, this subcategory should sum up to its parent in level 2 as well. So let's do a quick example on how to read the statistics. So for example, for this one, the highest fraction was the backend bound. So we first select the backend bound category. Since it's at 0.99 and the others are like way lower than that. So we move on to level 2. Since it was marked as a backend bound in level 1, we prune the other branches of these categories and only expand the branch of backend bound. And over here we see that it was a memory bound on this level 2. And then we move on to memory bound of level 3 of memory bound, where we see it can be marked as the level L3 cache bounds, which means the load miss were searched from the level 3 cache. So this example was from a workload trying to stress L1 to L2 data cache workload, so which says they are reading as well. So for evaluation, we try to find the answers to these questions. can we accurately identify workload bottlenecks so that we can validate that our implementation reveals the true bottlenecks? And can we detect mistakes in the gem5 configuration between real hardware? So we evaluate our implementation on the ARM use stress benchmark. It's a micro set of like 23 micro benchmarks trying to target specific points of pipeline to create bottlenecks. Unlike traditional benchmarks, which try to get a measure of overall performance, the benchmarks stress specific points in the pipeline, such as the front end, back end, or the branch predictors. We run our experiments on Golden Cove on our Neoverse V2 CPUs so that we see that our results are applicable to different processor types. In the real hardware, we get our results from using Perf and ARM telemetry solution, and we validate it using both system calls and full system simulations. So this is the first level analysis from Golden Cove and gem5. Here, the categories should sum up to 1. Green and retiring in green, best speculation in red, and front-end bound in purple, and back-end bound in blue. So the first 2 benchmarks are branch direct and branch indirect workloads, which stress the branch predictor. As you can see, we have correctly identified as a bad speculation benchmark. And the other 4 are like floating point division units, multiply and accumulate, L1 data cache, L1 DTLB, which we have again successfully identified as backend bound. And the last benchmark was L1 instruction cache stressing one, which is also correctly identified. So our analysis can correctly identify the bottlenecks. So moving on with the cycles per instruction stack. As you can see for the many benchmarks, our methodology could perfectly get very similar results as in the results from hardware. The cross-hatched bars are from the real hardware results. So for example, in the branch direct workload, we got a similar bad speculation percentage, but for example, in the floating point division one, it tells us that there's a possible misconfiguration in functional unit, or in the L1 iCache, even though we got very similar CPI with the real hardware, we had a much more bad speculation percentage, which tells us that there was a possible misconfiguration in the branch prediction unit. So moving on to our Neoverse results. Here we focus only on the backend bound workloads. As you can see, the results are very similar to real hardware, but there's a slight there's a difference in the floating point division and square root units. And thanks to the top-down methodology, we can see that the extra CPI in our simulations are due to backend bound, it's not coming from front end or the branch predictor in your processor, so you can focus on the backend bound. So we go back to our configuration and actually see that we have wrongly configured the operation latencies for division and square root units. So we correctly configure it and then run the simulation again to see that we now have a similar CPI as well as the similar top-down analysis results for both in the new configuration and our hardware results. So in conclusion, O3 is a complex core. It's hard to analyze, and there is no systematic approach to analyze the results. It is hard to configure, and therefore it's not welcoming for new users. And our top-down methodology, it provides a systematic approach for analysis, as well as it can be used to validate gem5 configurations, and also it decreases the analysis time significantly. So we believe the gem5 community can benefit from this implementation, and we want to upstream it soon. We have already created a pull request. We expect your feedback there. Thank you for your attention.
Thanks. And the first question of when are you going to push this has already been answered.
Yeah,
that's really good. Go ahead.
Yes, hello, it's me again, Joseph Rogers, NTNU. I find your results actually very surprising, especially given some lunch conversations I had. I didn't quite catch what types of benchmarks were you running to validate this? Were they just micro benchmarks? They weren't like full applications like spec or something like that?
No, we don't run, these results are all from micro benchmarks.
Okay, so I would love for you to try this on full applications because my understanding is that due to things like the not decoupled front end of Gem5, you would have very low IPC compared to native hardware, and this is not due to a misconfiguration of the O3 CPU, but more sort of. So I would be very interested to see what the analysis looks like in a more realistic application case like that.
Yeah, we're also working on running it on like some of the real server workloads from such as DC perf benchmarks to it. We will also publish these results as well.
Yeah, that would be fascinating.
Yeah.
Thank you.
Yeah, Matt's from Wisconsin. I'd actually like to take his point even further. It would be super helpful for us, in general, for getting the x86, ISA CPUs to work well. If you actually integrated your micro benchmarks in the gem5 resources, we have a big persistent problem with x86 with tests of all sizes. So if there's not anything secret or special or whatever in your tests, I don't have a question here, but I hope you'll consider doing that.
These benchmarks are from actually ARM's used test benchmark suite. So they're
Can you rewrite them to use x86 then?
sorry.
I mean, ARM and x86 have different memory consistency models. So like, how did you
So yeah.
change them to work well for x86?
So in those benchmarks, they both gave a like C code as well as the assembly for ARM. So we run using the C code.
Okay, so you didn't rewrite the inline assembly. Okay, that could be another reason, to his point, why you're seeing that behavior then, because the inline assembly often will generate much more efficient tight loops to test that behavior.
Yeah, we can also recommend that.
Either way, it's great. Yeah, it's very interesting.
Thanks.
Yeah, I'll back up the micro benchmarks. When you compile them, you see like have C code that's your micro benchmark. Oftentimes, yeah, the resulting assembly code is very different than what the C code looks like. And that like Carter did a set of micro benchmarks and we got really bad results with Gem5 because of a compiler issue, not because of Gem5.
Yeah, so in our experiments, like CPIs were like different for some micro benchmarks, but at least we could correctly identify the bottlenecks for all of them. So
yeah. Right. The meta point of the top-down analysis is amazing. Yeah, awesome. Okay, thank you very much.
Yeah, great. Thanks.